All right, Ben. What's going on today? We had a good conversation on YouTube about this topic today.
Last week, our video about that thing we talked about did really well.
You mean the bleepity bleep?
Oh yes, I love bleeping JavaScript. Yeah. That kicked off an interesting conversation in the comments, which you should go read, about styles of inheritance versus composition and that sort of thing. So that prompted us to do a video today. We're talking about types. I would call them classes. People a lot of time call them classes, but we're not going to do that for a reason we will
for JavaScript reasons
share in a minute. So let's dig in. When we're talking about types, what are we actually talking about? What is the problem that types solve for us? When you're designing a program, why do you even care about types?
The number one thing I think of is because we hear all the complaints into JavaScript land is the IDE. It doesn't know what this thing is, so it can't help you finish your sentence.
Yeah, so I could say var b equals something, and that is an A, by the way. My text editor has no idea what B is.
Or what it's going to be, or how it's going to act.
How to deal with it, so programmer convenience. That's a good point. Where if this was Java and I said B is a new person, because Java is typed strictly and statically, Java knows what this B is, what it can do, and if I try to make the B fly, Java's going to throw a fit. The IDE is going to throw a fit.
So now this is one of the key reasons I think that Java did so well when it first was created, is because the IDEs could predict. Since it was so statically typed, when we had these types, they were able to predict what, you create these great tools and do refactoring. Refactoring in JavaScript is still a nightmare, but refactoring in these statically typed languages aren't so bad.
Yeah, so we'll say reason number one is control space. This is, I should give that a 1.
There you go. Well, I need a translator there.
I know. This says control space. Convenience for the programmer.
Yeah.
It's really helpful if your IDE knows what that is. Okay. Now, another reason, and from a computer science point of view,
I'm going to send over here since you're right.
Probably a better reason. Yeah, I just kind of stole the stage. Somebody once was making a bunch of objects in a program, and they noticed that a lot of these things had something in common, and programmers, we hate to repeat ourselves.
Right.
So, shoot.
Isn't that what our job is, to automate things, right?
Exactly. So, I should actually have something else up here.
It's kind of like our cookie cutter.
That handles all of that for me, and then I can get rid of it out of here and just do the more specific stuff.
Right.
Here, I can do squiggly lines or vertical lines and who knows what.
Right. So these things are inheriting this functionality, and we augment it.
Yeah, I make this, I say, hey, this is one of these, and it gets all that stuff.
So maintainability, it gets better, because now if Square needs some more things happening, we just write it up there, and all of a sudden 3 children get the use.
So there's number 2. I'll try to write more.
There you go. Well done, Ben.
Reuse. Any other reasons?
No, I think reuse you get the maintainability and the code reuse.
So types. That's essentially what we're talking about when we're. There's actually 2 ways to get at this reuse part. Okay. See, the one I drew, which I should have left there. I have one thing up top with some property, and then all of these things share that property out here. This is called inheritance. There's something up here that has what I need. So I'm going to subtype,
Okay.
usually subclass,
Right.
this thing and get all of this stuff down here.
Right.
That is one way to get it. That's called inheritance.
Okay.
Another is if you have a bunch of properties here. This is called composition, where I'm going to take these things and compose my new objects out of them.
Okay.
So this needs a circle, but it also needs a triangle, so we're going to do that.
Okay.
And I get my circle and my triangle.
So these things just live, well, these kind of, almost like this. Instead of being a circle and a triangle, it's almost like the box comes with it, right?
Right.
So.
And then this just needs a triangle, not the circle.
Okay, so let me just steal your thunder here, right? Triangle, not the circle. This one just needs a circle.
Right. And so we can draw that like that. This is called composition. In this case, all of these things are really specific. They do one teeny tiny thing.
Okay.
And then my new thing can gather all of that stuff up and make a bigger thing.
So you pointed out something really interesting is here in inheritance you start very generic and you get more specific on its leaf ends.
Right.
This is a little different. We're very specific and then we kind of go a little more generic. I guess it's not more generic, it's just we just kind of gather.
The object gets bigger.
Gets bigger, exactly.
Gets more responsibility.
So there's really no tree hierarchy in this.
Yeah. And with composition you could technically even take this and compose it over there and have some kind of...
So you're saying that this object has this inside of it?
Right, we could... You're not going to be able to see this.
But trust us.
But, all that stuff is in there. So let's dive into inheritance real quick. I'm going to give you the marker.
Okay.
And say go for it.
Okay, so what...
Sorry, back to what you were going to say before I so rudely cut you off.
Well, inheritance, we have two types, right? The classical and the prototypal.
Yes.
Right? So let's talk about the classical. The classical is static, so which means that these types are declared, they're written, and then at compile time, they're compiled down to a static type. And augmenting these types is pretty much impossible. Now in C# they have something called extensions, but
Objective-Z has a similar sort of thing.
Right, but what they're trying to do is they're monkey patching. They're trying to get around this whole type system.
Program.
So so we keep erasing these things. They're gonna get really sick of this, but this is the typical hierarchy tree. I noticed something that you did before is with the typical classical inheritance. The methods and the properties right up here, they're inside this parent class, the superclass. These just then augment the new additional things, right? But what's interesting is that in prototype, it's not entirely true, because what happens is this whole thing here gets copied into this class.
Yeah.
So it basically consumes it and then adds stuff to it,
right? Everything here, when you instantiate this thing, this whole thing gets copied, and then, and
it lives inside here. So this actually has that. So it's like almost like in our code it looks hierarchical, but when it gets compiled, it compiles down to this.
You defined a cookie cutter basically, and
stamp them out. The difference is now, if we look at prototype, what really happens in prototypal inheritance is we're really going back there for those properties. So for example, this inheritance style, they don't share the same objects. Each instance has its own specific properties and methods. They probably do share methods inside of the compiler. I'm not sure exactly how that works.
You can do
but
static properties and static methods, and that's really a little strange.
Okay, so but in prototypal inheritance, like we were discussing on the comments, it's really nice. It's actually nicer on memory in some cases, and especially in JavaScript's case, because if you're to go the classical type, try to force JavaScript in the classical type, what happens is when you put everything in the constructor, it creates every single one of those properties and those methods again. Even though they're the same methods, they're the same properties, it's cranking up, so your memory goes up. With prototype inheritance, you get these properties and these methods for free. We have one of them, And then they have, these guys use those methods and those properties.
Or to put it another way, with classical inheritance, the type is defined by a class
Okay?
at design time,
Correct.
and that's static.
Correct.
With prototypal inheritance, the type is actually defined by an instance of an object
Right.
at runtime.
Okay, so this type is class, right? Should we say that?
Yes.
Is a class. This type is an object.
And what you're essentially saying here is, I have a car, and it's actually an instance of a car. You can get in and drive it around, so
Right.
to speak.
Okay.
And then down here you have your Mazdas, your Toyotas, and your Fords, and they inherit all of their common properties from
that car instance.
From that instance. So if I go and change something on this car instance, it will change down here. That does not happen with classical inheritance.
And so you can augment these on the fly. You can start putting properties and methods on this prototype, and all of a sudden
You could say,
you got it.
all of my cars now have a parachute. And
poof!
they would have one.
They'd be falling out through the sky, 50 cars.
They
You
would
could just prototype, give them a parachute, and they'd all float safely down to Earth.
Yeah.
Okay.
The prototypal inheritance is maybe not what you're used to, but it's a lot of fun. I really like it. JavaScript does this because JavaScript is almost completely dynamic.
Right.
There's almost nothing static going on in JavaScript. And we're not going to spend a whole lot of time on this versus this in this video.
Right.
But it's worth looking into, and I really like prototypal inheritance.
Right. So now now that we've talked about the different types, let's actually go into the example of inheritance, which is a good example that you told me earlier. You take it away, Animal Kingdom.
All right. So with inheritance, when you sit down and start solving your problem, you essentially have to start thinking really big, because remember, all of these objects are going to inherit from bigger objects.
Right. So more generic, right?
If you want, yeah. So I'm going to say, well, I know that I'm going to be dealing with things that are really a lot like animals.
Right.
So I will define an animal class. Now this animal class by itself isn't very useful. You can't say, I want to do animal. What are you going to get?
Yeah.
You got to be more specific than that.
Okay.
Well, there's lots of different kinds of animals. So I know that I have birds. I know that I have fish, and I have mammals. Okay.
Yeah, that looks good.
So there's one level down.
It's working pretty well.
Now, we'll dig into mammals. There's vertebrates. Well, I guess that's even a little more generic. Anyway, there's mammals that stand up and walk around like people.
Uprights, okay.
We're going to jump straight down to species and say people,
Okay.
dogs, and my kids really like to watch a certain cartoon, Phineas and Ferb,
which I
in
really
which
like.
there is a character playing Perry the Platypus. So
we've got a problem here.
we got a problem. What defines a mammal? It's hairy.
Right.
We
thought
the mothers produce milk.
Right.
And they give live birth. But not a platypus.
Yeah, we're in trouble now.
So now I'm going to come in here and put my platypus in here, and it
it goes over to a bird a little bit, doesn't it?
It's a little bit animal and a little bit bird. With classical inheritance, this is a problem, because if some subclass doesn't fit entirely inside of any of the superclasses, you have two options. Well, okay, I'm not going to leave it at two.
There might be more.
You have some options. One, you can go back up the tree and make something higher up more general.
So you shift the whole tree.
Yeah.
Just shanks it down.
So I'm going to draw a tree now. We'll say this is an animal, mammal, and then all your stuff down here. Well, we hit a case where this didn't hold up anymore, so now we need to
put it. Yeah, how are we going to do that?
Oh shoot. See, every time I wiggle up here on the tree, everything down below it shakes.
All the leaves are shaking here.
So now I have to take that property out of the mammal, or not out of the mammal, I guess. We have to say there are mammals that give live birth and mammals that lay eggs.
Now we got a problem here though, because most mammals give live birth.
We're gonna have a whole bunch of mammals over here.
What's the one
Down
case
here?
One case. Oh dear. So platypus gets special. Perry gets special treatment. A special branch.
No, that I don't think anybody would agree that that tree looks very good.
Okay.
So, but we've been doing we've been doing inheritance forever and ever. It's a good thing, right?
Right. Well, in some cases, I would think so.
Obviously, we've misused it here. What's the problem?
To me, it's just too deep. I mean, I don't know. I prefer composition over deep inheritance.
Yeah. So this is a problem with inheritance.
Right.
You're going to run into this case, the platypus case, and the other option you have is to try and override that property on this class.
So instead of live birth, you have to say, oh, these are really eggs now.
In this special case, this happens. But if you do that, you're never going to be able to inherit from that.
So
Again,
what's really kind of deceiving though too is if you did that override, and remember if you have types and you want to do an ISA check, right? Is this thing a mammal? And you're expecting that all mammals give live birth. Well, you just ruined it because you overrode it, and really, well, there's one case you're going to stream along in your program is going to hit this platypus and it's giving you back eggs. And you're expecting a mammal back.
The special case is the nemesis of a good design.
Right.
So if you're trucking along on this design and you hit a special case, there's a problem.
So we used to say when we would work together is if we found a true principle that we thought was a good pattern, and the pattern was really good and it was chugging along, and then we hit 98% was perfect, and then we had this 2% not perfect, we would scratch the whole idea and say we've designed it wrong, let's redesign it. Because we knew that if it didn't work for every case, then we're doomed.
A true principle is always true.
100%.
Yes. So, and that's not to say that inheritance is a bad thing.
Right.
It's just the wrong answer to this design problem.
Correct. So let's talk about that.
We need to do something else.
So what's interesting is when I joined the company that you can erase this, but when I joined the company that we both work for now, everybody was against having a person object. There was no code reuse at all.
They were against inheritance.
They were against inheritance, and they had good reasons to be. And the reasons why is because we had 3 types of systems that needed a person, and they needed to act on a person differently. And each one of these systems wanted to have different methods. They wanted to say, I want to get the location that this person's at, and I want it based on this thing. And so they said we could not, there's no commonalities between it all, so they just had their own instances of a person, and you never knew what was going on. We'd change it in one spot and forget to change it in another spot. It was a nightmare. But the reason why they said they didn't like it is because of the horrible cycle of deep inheritance. Because what they were thinking is what we need to do is we need to create a person object up here that's general, right? Then we need to subclass it out and have all these different other functions. But what they found is it just got messy because some people would come up here and change this and have effects all over down here. And they got really upset about that. So what we ended up doing is we realized early on that composition can solve this problem. And the real life, well, what we ended up doing is we first off took most methods off of the person completely. We realized that every application was so different that you couldn't possibly build a person object with every type of method on it. You know, like in this specific application, we want to go find their home location. Well, you build that method inside the object, now it's attached to every object. This is bloat, even though only one application is using it and 11 other places are carrying it. So what we decided is, okay, let's strip down the person down to data points. So I've realized that where we use most inheritance anyways, is it's usually with POCOs. And then we use composition.
Plain old class objects.
Yes, plain old class objects. So what that means is there's no methods on them.
Yeah, you said you ended up taking all of the methods off of the person.
Yes.
But every person still has a first name and a last name and a birth date and an employer.
And we now share the same person object, right?
So we are getting that reuse by inheritance.
Yes, we are. Then what we're getting, though, is now we're able to pass this person, right, to a controller who acts on the person and saves the changes. So now each application can have a controller and act on the person. Now that's what we would call composition. That then leads us to another thing too. Is we had a problem in our company, and maybe your company's like this. We had a person have multiple responsibilities. If you're an employee and a manager that works with a class with just inheritance altogether.
Yeah, we can say type employee, and let's have a person.
Okay.
And as a subclass of employee, we have manager, and we can have an engineer, and we can have a janitor.
And so for our company, not only did we need to know these positions, but we needed to know when they were in these positions. And when they left from these positions. So they needed to be expirable.
And there could possibly be a case when an employee is both an engineer and a janitor, or an engineer and a manager.
Yes.
And so how do we put that in our tree? We have to say our new employee equals a new managed engineer.
Right. You'd have to combine it somehow. This is where you get to where you're talking about you have to reshuffle it. Where you'd have to, since we had created this new problem, right? Because it really needs to be a combination of those two, where they didn't intersect before.
So the solution with inheritance is to make a new object.
Right. Ingeniator.
Ingeniator.
Right. So that's what and that becomes ugly and unbearable. And then it's duplication in your database too.
Exactly. It's going to obliterate the reason that we did all of this, which was code reuse, because I'm going to have to copy the code out of here and copy the code out of here and paste it into there.
Right.
So, special case, obvious problem.
So this is that 98% that we talked about. It almost got us there. But what we realize is that we do know that people exist. We work with people every day.
Right.
But the key thing that was different about them was that they had different roles. So you could be an engineer and a janitor. So what we did, we used the composition with inheritance. So what we did is we said, okay, we're going to use a person, and this is going to use a has-a principle, and it's going to have a property on it that's called a role. Now over here, we're going to have another class that's called a role, right? And this is going to be an is-a. And this role, so roles, I guess, thank you, it's an array. This role, everything is basically a really shallow inheritance. We have now a role of janitor. We have a role of manager. And a role of, engineer?
Mm-hmm.
So now we've solved the problem. What we do is we say, okay, they have a bunch of roles, and they can now be all three of them. And now we can even expire them. So now they could have been an engineer twice, and we knew when they were an engineer because they had a start and end date.
Mm-hmm.
We have a history. We can know, in our company, it's really critical to know when certain people were in that position for legal reasons.
Right.
And so this is the way that we manage that complexity. So it's the combination. Inheritance isn't evil, and composition isn't evil. It's that if you create this harmony between the two, it's a beautiful symphony.
Yeah, I think it's important to point out that right here we have two inheritance trees, but then we're combining them into a compositional structure.
Right.
That's really powerful. When you think about it, even if you're a die-hard, all-the-time inheritance type of person and you're willing to deal with this special cases and try and implement multiple inheritance as some people do,
right.
You're still using composition. Because when you define an object is really just a composite of other types.
Right.
That's composition.
So you can't if you're saying that you're a diehard, you can't say that you're a diehard basically.
I would say there is such thing as pure composition, but there is no such thing as pure inheritance because every object is going to be a composition.
What you said earlier is that composition is what created inheritance.
Yeah, I'm not totally sure on the history and the time.
Well, no, I know. I'm sorry. I put words in
yeah,
your mouth, but essentially is
composition
that's what
came first.
Yeah, that's what kind of drove the point of inheritance was a composition. They wanted a way to compose types.
It's just a different style of a different method of reuse. I think during the Java years and C++ years and all of that, we maybe got too infatuated with this idea of inheritance. I can remember my brother had a chart of C++ objects, and it filled the wall. And clear up here at the top was the object. And then inheriting from that was this type of object and this type. And you could go 6 or 7 or 8 or 9 or 10 or 20 layers down. And even, I'm going to murder his name, Bjarne Stroustrup, who is one of the leaders in the C++ community, says these deep inheritance structures are a bad thing.
He created it, by the way.
Oh, yes.
Yep.
So in terms, I guess just to wrap up, in terms of freedom and flexibility for you as an engineer, it makes sense instead of starting general with a big piece of your problem and trying to work down from there, if you've done that, you know that always goes wrong. It makes more sense to approach your objects like you approach a problem. You start with the small pieces, solve the small problems, like how to fly, how to lay eggs.
Or be hairy.
Or be hairy. Or, let's see.
Walk upright.
Or walk. Now from there, you can say, oh, I need a bat. And I need a person. That's just shorter right than human. I'm not being sexist. Walk and hairy. And I need a sparrow. So I'm going to take lays eggs and flies.
What this ultimately tells us is this is like really defensive engineering. It allows you to tackle the problem at hand immediately without knowing everything that could possibly go. For example, with the tree shaking that we talked about with inheritance. We worry about that. We can't do that to our database every day. So what we do is we use composition to solve those problems. We use composition to not have to know about everything. We just take the problems at hand. We know about 3 of them now. There may be 1 trillion in the future, but we can compose them later. Yeah. As long as we, like we did with the person and the roles. We don't know of all the roles that are going to come up in the next 100 years, but we do know that we can facilitate it. And that's the key as an engineer.
In our database, the way we've structured our objects, we do have an inheritance hierarchy that goes down 4 or 5 levels deep. But we do that because in some cases it is important to be able to answer the question, is a.
Right.
And I can't think of an example off the top of my head.
In ORM it's important for me.
Is an employee role a role? Yes. And I need to know that because when I'm hooking up the relationships, I know there's a relationship between a role and something else.
And
therefore, there is a relationship between an employee role and a person. And,
exactly.
And that's important. But the pattern that we've seen is that the inheritance works best on fields. So the types that inherit are just purely fields. They don't do anything.
Right.
The place we use, if you need to make that person dance, you don't put it on the person type.
Right.
You have a dance behavior that you put into the person type.
Correct.
And this is called, it's super easy and a lot of fun to do in JavaScript. You just say apply.
Yep.
And I love it. And there's a video that we made about that. I forgot where I was going with that, but
well, it just allows you to compose later.
Oh, mixins. They're also
mixins. That's what it's called in Indian. They say that.
Often called mixins too. Anyway,
I think that we got the point across, and we are big advocates of both. We can't say that we We were strictly one or strictly the other. But what's interesting is when you engineer these things and you sit and you talk with your group, and you'll notice when you're doing the wrong thing. When inheritance is dying and the tree's shaking, use composition and it'll save your life.
Yeah, and if you end up with objects, like this whole group of objects who all happen to have a first name and a last name, field types, or fields, you should think about inheritance.
Exactly. All right.
I think that's it.
Thanks.
Thanks.